Okay, good morning everybody, and welcome to the last session on EDSP this year. So last time we started with all-pass filters, and we saw that all-pass filters basically can be seen as only affecting one phase. So we have a constant magnitude of 1 for the entire frequency response, but we have changing phases. So for instance, if we have a pure delay of d samples, this pure delay would be an all-pass filter, because it passes everything unattenuated and it changes the phase. And we saw in this example here that we can build fractional delay filters in this way. So this d, this delay, this pure delay, doesn't have to be integer valued, but it can be any fractional number. And we obtain such a filter by just taking this ideal frequency response and apply the inverse in DTFT to it, which in this case is quite simple because it's mathematically quite a simple formulation. And what we get is then this sinc function, a shifted sinc function. So it's not centered around 0, but centered around d. Right? So it's shifted by d samples. But since it's infinitely long, we also need to window it to make it implementable. So in this example, we applied a sine window of some desired length, here L samples. And then we have our simple fractional delay filter. We can easily apply it in Python, as you can see here. So this is then our FIR impulse response, finite impulse response, and here I make the implementation in IPython. So last time I had problems with quotation marks, so now I fixed the quotation marks to be quotation marks which are accepted by Python. So we can test it. Let's go into our German shell, start IPython. Minus PyLab. So here we see that we are now in the Python command mode. And then I can just copy and paste this entire program. So just copy everything here. And hopefully now it works with the correct quotation marks. So I have two versions, one short version of the filter and one long version. Copy. Paste. Yes, so now it works. So this is the last window. So here you can see the plots. So here in the beginning you can see the blue is the sine window that we apply. Then the sinc function is this orange. So you can see this is the sinc function over this interval here. And then when you multiply the two, you get the windowed sinc function, and you can see that it's getting smaller towards the end. So it's faded in, faded out in this way. Right. So then the next window here is a test signal. So here the blue is a ramp function as a test signal, so then it flips back to 0. This makes it easier to see that we have a correct shift. Right. I could also take a sinusoid as an input, which is then easier to shift actually, but here it's easier to see that we get the correct shift, and it's also easier to see that we get artifacts. If you just have one sinusoid, then it's not so easy to see artifacts. So here you can see when you extrapolate, you get it about, you cross the x-axis at about 5.5 samples. Well, it's actually 4.5. So you should land by about 4.5 samples here, which is the desired delay. But you see we have also artifacts, like these ripples in the beginning and some ripples here in the end. So it doesn't actually look so great. It's doing the shifting, but it also has visible artifacts. So that's why we tried another attempt. So what do we do if one filter is not good enough? We make it longer. So this is what I did here. So now I have a window of twice the length, So now I have the window length of, I think 20. And here you can see the resulting filter. So here is the sinc function itself. Blue is the sinc function again. Right? And in orange you see the windowed sinc function. Again, you can see that it's having this fading in and out. Right? So it gives it better properties. But you can also see now we have more ripples to the sides. And here you can see how it affects the shifting. So now here we have a shifting by 9.5 samples because we have a longer impulse response. So we need more samples to make it causal. And here you can also see when you extrapolate this line, it should end up here at about 9.5 samples delay. So there's this point shifted to this point here. And the rest here is the ripples from our sinc function, the windowed sinc function. So again, you can see those ripples look somewhat different, but they're still there, right? So it's actually not so great. So even though we have now a longer filter, it's still not so good, basically. So I'm still not quite happy with this filter. Too many distortions. So then we can also take a look at the frequency response using Frexi. So first, here are the plots. Now in the slides, the plots that we just saw. Yeah, so this is what I just said, right? So the height of the ripples remains similar. But we can also check it in the frequency response, in the frequency domain. So we use our Frexi command, which is in Moodle 2. Like, remember, this Frexi in Moodle 2 just additionally contains the plot functions. So it's just convenience. Basically, it's the same as the sidebar. So I imported this Frexi function from Moodle, and then I use it. I apply it to our filter here, so it's using Frexi, so this is the library, .frexi, this is the function inside this library. And here you can see the argument. So this is the numerator, and then this is the denominator, which is 1 in this case, because we have an FR filter and not an IR filter. And here you can see the resulting frequency response. So what do you think about this frequency response? Does this look like an all-pass filter? Yeah. Why does it look like an all-pass filter?
Because it has a non-stop but between 0 and 5.
Yeah, let's say mostly. What about the end here? The end doesn't quite fit, right? It should be constantly 0 dB over the entire frequency range. And here in the end, it deviates from this ideal wish that we have. Right? We wanted to have all 0 dB, no attenuation. 0 dB meaning gain factor of 1. Right? But here we see we do get some attenuation here towards the very high frequencies. So this again comes because we shorten our sinc function. Right? We only take a limited length over 20 samples, and that means we make an error. Right? This is not the idea. We make an error because we cut at the ends, or we fade out the ends, and we become FIR. So this is one of the errors that we make. The very high frequencies don't survive. Right? So it's not so great, and this is actually also what we observe in the time domain. We get errors, and here also in the frequency domain, also we get errors. So what about the delay? How do we estimate the delay here in this plot? We wanted to have this 9.5 samples delay. How do we find the delay here? Well, remember, the delay is the negative slope. Right? So this is actually what I wrote down here. So in our case, when we have a delay of d samples, right, a pure delay, then the angle, here, this angle, can be written as minus the delay d times the normalized frequency omega. Right, so we have a function here, a linear function, at least for this ideal case of a constant delay, it's a linear function. Right, and that means this delay is simply the negative slope of this function here. Right, so we just need to determine the slope of this function. So how do we determine the slope here? We can just try to take one sample. So maybe for that it's better to use the mouse. So I can just do that in my terminal shell here. Copy. Paste. So here we have it. So this is now our frequency response of our filter. And we can, for instance, go here to the beginning at some point. Say here at this point, you can see here on the right hand side, here those small numbers give me the precise coordinates of my mouse. So then it's easier to read than from the plot itself. So here at this point, I should be at minus pi, because this is where we get the wraparound. So it does this wraparound at minus pi. Right? So this is minus 3.14, and you can see minus 3.1. Yeah, good enough. Right? I'm not so precise with my hand and the mouse. So 3.1, and then we can also read out x equals 0.325. Let's say 0.32. Right? So this is 0.32 at this point. So now we have 2 points, x and y, and we can compute the slope from it. So let's try that. Yeah, so first this is what I just said here about the loss at high frequencies. To estimate the obtained delay. So we do that for checking or for verification. We use the mouse, go to y equals minus 3.14, which is the first wrap around point. And read out position x equals 0.32. Was that correct? Was it 3.2? 0.32? Check. Oh, so. Yeah, 0.32. So then we get from that, we obtain the delay d equals minus y divided by x equals 3.14 divided by 0.32 equals, what does it equal?
9.8.
Oh, you already computed it? Great. So let me try it here in my IPython. 1.14 divided by 0.32. Yeah, so we are ending up at 9.8. Yeah, this is roughly our target of 9.5. Indeed, roughly the desired 9.5 samples delay. from the numbers is not so precise. Right? So that's basically all we can all we can expect. Yeah. So basically, it gives us the delay, but it has this attenuation at high frequencies. Right? And this attenuation is not so good. So here we have true for fractional delays. Yeah. But we have this attenuation at high frequencies. So hence IRR filters can improve our performance. So that's why I now included this IRR fraction delay filter design. And I have it from these papers and references in it. They describe a quite nice way to design fraction delay filters. So the math behind this is a little bit tricky. So instead of writing formulas, I am directly presenting you the Python code, because the Python code is about as obvious, maybe even more obvious than the formulas. So here I'm defining a function. So this function here takes as an argument tau, and tau is the delay. Right? We just call it delay, like t. So it produces two arrays, A and B, and these are the coefficients for our IRR filter. So B for the feed-forward coefficients and A for the feedback coefficients, as we had before. Right? So this coefficient from this desired delay tau, it computes those coefficients, and those coefficients are then an all-pass filter, an IRR all-pass filter. So we start here with an L, which is the length of our filter, which is basically the rounded up delay. Then we make a time axis n, going from 0 to up to but not including L. And A0 is starting with a 1, an array consisting just of a 1. And then we continue to define A as this array using this cumulative product. So this is kind of the tricky part here. Basically, it takes the product of the consecutive product of this array that is defined here. So we have n minus n, which is an array, and then we have n minus n minus tau, which is also an array. So here we do the multiplication of those two arrays, and here we do a multiplication again of those two arrays, and then we append those two. So it's, as I said, it's kind of tricky, but in the end it gives us a nice IRR filter. Yeah, and B is simply the flipped array A. Right? And this leads then to a magnitude of 1. Yeah, so we give it the name all-pass delay filter. I'm not sure why it's in 2. Yeah, so we put it in this file, all-pass delay filter.py, and this file not only contains this function, but it also contains this main function here, which tests it. Right? So this is always a good strategy to have functions in a file, but then also to have a main section which is only there for testing. So when you then use the functions in some other program, you say import all-pass delay filter, and then it imports the function that are defined, but the main section is not executed. Right? This main section is only executed if you call this file from the terminal shell. Right? And this makes it very practical for testing purposes. So you define the function in a file, you use it in a different file, and when you want to test it, you call this file itself, and then it executes this main function. So I did it here with a delay of 5.5 samples. So just a fantasy number, 5.5. So I'm again taking our test signal, a ramp. So it goes up and then jumps back to zeros. Here the remaining zeros. And then I apply this filter here as L filter. So this is coming from SciPy signal, SSP, you see here. And so it uses our linear filter. Here B is the feed-forward part, A is the feedback part, computed from our function, and X is our test function. So out comes Y, and Y is the delayed version. So now we can execute it. So I can do that here, copy. And here I don't need IPython because I have a function. So here just say Python 3, I was already in there. So I just paste it. Right? So this is then my command. I execute it, and this is what we get. So what do you think? It still has ripples, right? So you can see here the delay seems to be approximately correct. So when you extrapolate to 0, you end up here. So this is roughly 5.5. Okay, so we have a shift from here to here, which is about 5.5 samples. So that's fine. So this piece here looks fine. But then this here is it's not exactly the original, because the original jumps back to 0. So here we get ripples. Here we have some ripple, but here it's less ripple than in the previous approach, right? Remember, previous we had more ripples in the beginning. So here we have now less ripples in the beginning, but we still have ripples on the other side. And this is actually a property which is suitable for the ear. So if you have audio signals like clicks from a castanet and you want to shift them, then this is good because this reduced number of ripples in the beginning means we don't have pre-echoes. The ear is very sensitive to artifacts appearing before in the signal, but less sensitive to artifacts which appear behind. Because the ear also has this kind of IRR property. It rings behind but not before. Right? And this is basically the same that we get here with our all-pass IRR filter, that it has ripples behind but not before. Yeah. So in that sense, it's a more practical filter. So here you can see it again. So altogether, we have now fewer ripples, so that's nice. We can also plot the frequency response in this plot. So what do you think of this frequency response plot? Yeah, why is it all pass? Yeah. So here you can see 0 dB, and here you see 0.5, but it's 10 to the minus 14th. Right? So this is basically rounding errors here. Remember, Python has an accuracy of up to 10 to the minus 16 anyway. So this is on the order of the accuracy of Python. So this is rounding error. So this is actually quite precisely an all-pass filter. So this is actually good because here in the end we don't have an attenuation. So it also delays high frequencies. Great. So that's a big plus here. So here in the frequency response, this actually looks much better than our previous filter because it delays all frequencies up to microhertz, up to and not including microhertz. So then we can also estimate the slope. Right. So here, take this piece here, and I did actually did that before. So So here we can see, so I go to omega equals 0.5, so again a point which is easy to spot, right? So this is x is 0.5, and then the y, I hover with the mouse above it and I get a minus 0.28 radians, right? And then we get d as minus angle divided by omega, so that's 2.8. So the angle was minus 2.8, so it's 2.8 divided by 0.5, and that's 5.6. So you can also see here 0.5, and this is about 2.8. So here you cannot see it so precisely, so you actually need the mouse to hover over it, just to get this number 2.8. Yeah, so indeed we get roughly our 5.5 samples delay. So this deviation is more like the limitation of reading out precise numbers than the actual filter. So fits nicely. Yeah, makes sense? So this gives you actually quite a practical function to do fractional delay. Right? So the window sync function also works, but this works better. And so in case you need fractional delays, you can just take this function. And this is actually also something that we use in some of our research projects. For instance, for separating voices from a stereo signal. So we have two microphones, and we want to separate them, and we do that by estimating the delay between the two microphones. And the delay is not always integer values. In fact, it's always float. Right? And for that, we need this fractional delay. And we need to have it precise because we want to cancel one voice from the other microphone. So this is actually quite a practical application. Yeah, so then we come to a simple IR all-pass filter. So what we just saw was not so simple. So simple means we have just one pole and one zero in the Z domain. And we can write our transfer function with just one coefficient. And so A in this case is just a complex number, and A over bar specifies the conjugate complex number. So you can also see that you get something like this time reversal that we just saw. So here we have 1 minus A, and here we have 1 minus A, but here is Z to the minus 1. So here the lower coefficient is minus A, and here the higher coefficient. So you can also see it as like this flipping of coefficients that we just saw in the fractional delay filter. Right. And you can also rewrite it here by factoring out this A as having the 0 at 1 over A bar, and here you have the 0 at A. Right? So each are at conjugate complex positions. We have a 0 at Z equals 1 over A bar, conjugate complex. Right? And you have a pole at Z equals A. So when you do this flipping of the coefficients, you get the poles and the zeros at conjugate reverse locations. Yeah. So, for instance, if we have A equals 0.5, then we have the pole and the 0 on the real axis. Here we can try it. So here we have the two coefficient arrays for a filter. So this is the feed-forward part. You can see 1 divided by H conjugate complex. So here dot conjugate is doing the conjugation, which here doesn't matter because A is real valued, right? But it would also work in this case for complex A. Yeah, and A is here our pole. Right. So then we can plot it using Z-plane. This is a function which we also made ourselves. So this is the function which is in Moodle 2, and it takes the locations as argument. So actually, these are the locations. This is not necessarily the input of the filter. The filter has actually one entry missing for A. So here we plot it, and you can see here we have the pole, and here we have the 0. So is this filter stable? Why is it stable?
Because the put is
Exactly. So this is inside. So what about the inverse filter? Inverse filter would be 1 over this filter in the frequency domain. So a filter that would cancel this one. Right, so if you have h of omega times 1 over h of omega, cancels it. Right? So this would be kind of like a equalizing filter. So what about the corresponding equalizing filter to this filter? Would that be stable?
so
Why not?
Because the pole will be the 0.
Yes, right. Because then here the 0 would become a pole and that would not be stable. Right. Okay, so here we have this particular kind of filter. Yeah, and we want to see if the magnitude is really 1, right? We didn't prove it so far. And you can see that if we just rewrite our frequency response, which we just saw here, actually we replace z by e to the j omega, right? So that we get the frequency response, so that we evaluate this expression on the unit circle. Right? We had h of z, and if you want to see the magnitude, you need to replace z by e to the j omega, evaluate it on the unit circle, and then take the magnitude. Right? So this is what we do here. So we replace z by e to the j omega here in this formula, and then we can actually factor out this e to the j omega here, and then we get this expression. Right? Can you see that? It's just factored out. And then when we take the magnitude, what's the magnitude of this one? And the first one here, the magnitude of this factor is 1, right? Because it's always on the unit circle. It's just a pointer to the unit circle. Right? This is 1. What about this one here? What is the magnitude of this expression?
It's also 1.
Why is it also 1?
Because we have a complex conjugate and A, so they have the same magnitude.
Right, so actually this expression and this expression are both conjugate complex of each other. So here we have a plus, here the minus, so that means that this is also conjugate complex. Right? This is conjugate complex, this is conjugate complex, so altogether this is conjugate complex of this. And since this is a real number, that means this conjugate complex is this. Right? Because conjugate complex of 1 is also 1. Yeah, so we have a number divided by the conjugate complex number. What do we get? Yeah. And the magnitude of 1 is 1. Right? So everything is, magnitude is 1 here. The entire expression is magnitude 1. So that proves that this type of filter has magnitude 1 for all frequencies. And this is actually what we also saw in our IRR filter. It has those same properties with the flipped coefficients. And that means it has this magnitude 1. So here we can see that just using 1 pole and 1 0, we can obtain a magnitude of constant 1. We could also obtain more complex all-pass filters by using a product of this simple transfer function, perhaps with different coefficients. Right, so, like this IRR low-pass filter that we just saw, we have a higher order filter. And here we can also obtain higher order filters by just taking the product. Product with different A's. Did you have a question there?
No, actually
Does it make sense? It's
Yeah,
very
it
complex.
does. Yes, it does.
Yeah, it's actually a little bit tricky. But once you see it, that one is the conjugate complex of the other, then it's easy, right? You know. Yeah, so the more interesting part is now the resulting phase of this filter, and we could derive it. We could also take a look at this book here, Oppenheim-Schaefer, Discrete Time Signal Processing, and there you can find this derivation here. So this is the formula for the phase of this simple IIR filter. Right here you can see the phase function. And you can see this phase function is nonlinear. Right. Actually also the phase function of our little IIR fractional delay filter was also nonlinear, except that we didn't see it in the plot. It's slightly nonlinear. So here we can see the closed form expression for the phase. And yeah, so here you can see the normalized frequency which appears here, and then this theta and r comes from rewriting our coefficient a here as r as the radius times e to the j theta, which is the angle. So we rewrite this complex number as the radius and an angle. Right. So the r and the theta come from the a. Yeah, so far we assumed the phase to be linear dependent on the frequency, which means phi would be minus omega times d. And here we can see it's not really linear anymore. With its sine and arctangents. So for instance, we could use curve fitting with theta and r to obtain a desired fractional delay in some desired frequency range. So now we could use a to obtain a desired delay in some frequency range. For instance, at low frequencies. Or we could basically try different r and theta to see if we get the desired delay. Yeah, we can also plot the resulting phase over the normalized frequency and compare it with the phase of a delay of one sample, factor of z to the minus 1 in the z domain, which would be 5 omega equals minus omega. And here I plotted a equals 0.5 and a equals minus 0.5. Yeah, and here this sentence also tells you the connection to our previous example with the fractional delay filter. Right, the previous IR fractional delay filter was basically using this factor, except that this frequency range where it's usable is quite large. Yeah, so here you can see the effect for different A's. So the red line corresponds to a delay of one sample. And then you have the blue and the green, and one is 0.5 and one is minus 0.5. I forgot which is which. So here the blue is for A equals 0.5 and the green is for A equals minus 0.5. So here it's minus 0.5. And here you can also now see the nonlinearity of the phase. Right. So this is actually much more nonlinear phase than in our previous fractional delay IR filter. And you can also see this way we get different slopes. And remember, the slope gives us the group delay, which is the delay for this certain frequency range. So for instance, here in the low frequency range, right in the beginning, we have this slope for A equals 0.5 and this slope for A equals minus 0.5. So the slope then gives us the delay. And that shows you by changing A, we get different slopes and hence would be able to implement different fractional delays, at least here in the low frequency range. Right, so this would be a very cheap solution if we are only interested in the very low frequencies. Yeah. And in the beginning and the end are the curves are identical. Yeah, and if we set a equals 0, indeed we become a delay of one sample. Right? Yeah. So indeed it behaves very similar to a delay. And hence you can use it to implement fraction delays using different slopes, implementing different slopes, which provides us different loop periods. Yeah, for instance, the green curve for a equals minus 0.5 and frequencies below about half Nyquist has a slope which is about 1/3 of the slope of the red curve for delaying of one sample, and that means we have a fraction delay of about 1/3 sample. Yeah, so there's also this is also a nice reference for fractional delays here in the IEEE Signal Processing magazine. It actually gives you a nice overview of fractional delays, splitting the unit delay. And they do it with those approaches. Make sense so far? So now we have practical tools for fractional delays. Yeah, you can also use this all-pass filter for frequency warping, which is another application. So for a equals 0.5, which was the lower blue curve, we observe a stretching of the low frequency range, where a small part of the low frequencies stretch over the wider phase range than the other curves, because it falls down quickly. So if we increase our normalized frequency a little bit, it falls down more quickly than the unit delay. Right? And towards the end it catches up. Right? So it's basically also mapping the same input to the same output, that it hurries over the low frequencies. So yeah, you can see it. So here you have a mapping from input normalized frequency to output phase. And you can see they have the same range. So here the normalized frequency goes from 0 to pi, and the phase goes also from 0 to minus pi, except for this minus sign. So the same range, except for the sign. And here you can see in the beginning, the little increase in normalized frequency gives me a fast rise in the angle. And frequency warping now relies on the idea that we can write the angle also as a frequency. We can interpret this angle also as a normalized frequency. Right? And that means we map this frequency to another frequency. So we map this frequency range 0 to pi, 0 to Nyquist, again to 0 to Nyquist if we take the minus sign away here. And then we have a mapping from frequency to frequency.
So that is the phase we are remapping as phi as 2 pi f d.
Well, normalized frequency, right? Normalized frequency is 2 pi f divided by fs.
Yes.
Right? So pi would be the Nyquist frequency.
No, sir, you said you will be mapping the phase to a frequency.
Yeah, right. We basically interpret the phase, which in this case goes from 0 to minus pi, as a frequency.
Okay.
For this purpose. So remember, the phase doesn't have to stop at minus pi. It's just in this example, we use the phase just for this range from 0 to minus pi, because that fits nicely to our frequency range from 0 to Nyquist.
So if suppose the phase is say pi by 2, we map it to the fs by 4, am I correct? Fs by 2, am I correct?
There is no fs anymore in the normalized frequency, right? It's gone. So after normalization, you just have pi as Nyquist frequency.
Why do we map the phase angle with the phase? Why do we correlate it with the frequency?
Not yet.
Why I am asking why?
This is the basic idea which is coming up next.
Okay.
So far, it's really just the phase, right? Then here we could get the idea to interpret this as frequency,
Okay.
which we didn't do yet, but I'm planning to do next,
Okay.
right? So this is kind of the introduction to what's coming next. Yeah. Right. So here, a small part of the low frequency stretch over wider phase range than other curves. Yeah. For the frequency walking, we will interpret the negative phase as a normalized frequency. Does that sentence help? So for the frequency warping, we'll interpret the negative phase as a normalized frequency. So we will, which means coming up next. So first here, a plot of the phase of a simple all-pass filter. So here you can see warping phase, it just takes the normalized frequency omega, or W here, and this coefficient A. And then implements this formula that we just had from the book. Right. So here you can see R and defines R and theta as the angle of A, and it then returns this angle. And then we can just plot it. So here as the normalized frequency, we take this range from 0 to pi in steps of 0.01. Then we plot the frequency axis and the resulting phase with A equals 0.5. Here we plot it with A equals 0, and here we plot it with A equals minus 0.5. So this is basically the curve that we just saw. Yeah, so the phase and the output can also be interpreted as normalized frequency. That means its output can be the input of another warping phase function, right, if we take the minus sign. An interesting observation is that the warping phase function with coefficient minus A conjugate complex is the inverse of the warping phase function with coefficient A. It's negative. So this is what I did here to show you that they are inverse. So again, here the frequency axis. Here I'm now taking a complex valued A, 0.5 times 1 plus 1j. Right, so this has an angle of, what's the angle here that we get? What's the theta?
45
Yeah, I don't know, pi over 4. Right? So then here I'm applying this function, warping phase of warping phase. And in the first warping phase I'm using the coefficient A, and then I'm using minus A conjugate complex. Right? And then we're checking if this is indeed the identity function. So math by trying, basically. So here's the result, and you can see it's indeed the identity function. Right? Here's 1 mapped on 1, 2 mapped on 2, and so on. It's a nice straight line, the identity function. Yeah, so indeed, this is the identity function, and this shows that interpreting the all-pass is a normalized frequency warper. All-pass with coefficient A is inverse to all-pass with minus A conjugate complex. So strictly speaking, I only showed this for this particular A. We would have to try it basically with all possible A's. So this is just an indication that this is the case. But this is often also the engineering approach. You test the system at certain points, and if you have enough points, you say it's good enough. And this is also where you get, for instance, problems with object recognition in deep learning. Right? You feed it a certain object set, you test it on another object set, and when you're happy, you're done. And then somebody else finds an object which doesn't fit, and this is used for so-called adversarial attacks. Basically, untested objects which give unintended results. Yeah, but this is actually also a practical approach in cases where you cannot really do a mathematical proof. I mean, in this case, I could do a mathematical proof with some effort, but in deep learning, deep neural networks, it's usually not possible. Right? And then that is the only way to go forward. Yeah, so this is my proof by trial, basically. And yeah, then we have an example, all-pass filter. So the frequency response for A equals 0.5. And we can use fractional. So instead of the formula from the book, we can now use fractional to plot the phase. Right? Basically, the formula gives us a closed form solution. Fractional basically measures the result or computes it at different frequency bands. Yeah, so there we expect to see the magnitude to be constant 1 because it's an all-pass filter, and the phase angle like from our formula. So here's our all-pass again. Now we use B and A as our arrays for our filter. So A is 0.5. Then B, the feed-forward coefficients, is minus A conjugate complex, this part here. And then the next entry is the coefficient of the delay. Same for A. So here we have a polynomial. So the first coefficient here is for z to the 0, and the next coefficient is for z to the minus 1. So here we have a minus A. Make sense? So you're just reading out the coefficients of those two polynomials, put them here into this array. So the meaning of those coefficients is always coefficients of z to 0, coefficients of z to the minus 1, z to the minus 2, and so on. Yeah, so now we have the B and A, and we can again use our fractional and use B as the feed-forward coefficients, A as the feedback coefficients, and then it plots. And what we see here is magnitude-wise similar to what we had before in our fractional delay filter. So here again, tiny error, 10 to the minus 15, and basically precisely 0 dB for the entire frequency range. So this is what we already proved mathematically. It must be 1. And here we see the resulting phase. And here you can also see the phase looks quite different from our fractional delay filter. Right? So first it doesn't go as far, it basically stops at pi. And then we have this clearly visible nonlinearity. It has this bow here. Right? So it indeed looks like the closed form plot that we just saw. Right? Here for A equals 0.5. So that's a nice confirmation that our formula is right. Yeah. Right, so this is what it is said. We have this nonlinear phase. And now it would also be interesting to see the impulse response. And the impulse response is not as easy as in an FIR filter where we can just use the coefficient itself. Here we really have to use an impulse and feed it into our filter and see what comes out. And then this is what I did here. I'm making an input signal which consists of 21 zeros and then set the first entry to 1. Right, so we have a 1 followed by 20 zeros. Yeah, and then I use L filter with B, A, and imp this impulse as input, and then H is the impulse response of length 21. And then I can plot it here. Here's the resulting impulse response. So it looks kind of funny, right? It's not like a single function or something. It actually starts quite large negative, like almost minus 0.5, and then it jumps up to almost 0.8, and then it has an exponential decay here. It's kind of a fun function. Yeah, so we have a first non-delayed sample. Not at 0 yet, but at roughly minus 0.5. So this can be also seen by plotting the first elements. So not using plot, but just printing it. And here you can see it actually is precisely minus 0.5 and then jumps to 0.75. And here you have this exponential delay. Yeah, and this second element here corresponds to a delay of one sample. So here you can see actually the biggest factor here is for a delay of one sample. So what you can see here is that it's dominated by this one sample delay. But there's also samples going back into the past, exponentially decay. So here, this exponential decay. And this means not only past samples go into our filtering, there's a typo here. Also more past samples and even the non-delayed sample with a factor of minus 0.5. So this is actually the current sample, which also plays a role, which is different from a delay of one sample. Right? If you have a delay of one sample, then it's just this and the rest would be 0. Here we have other samples playing a role and even the non-delayed one. Yeah, and this non-delayed sample is actually a problem for the so-called frequency warping, which comes next, if you want to use frequency warping in IRR filters, because if we apply this all-pass in a feedback loop, we would have a delayless loop, which is difficult to implement. But with FRR filters, this would be no problem. So now we come to the actual frequency warping of filters. So these properties of the all-pass can now be used to warp the frequency scale of a filter effectively by replacing e to the j omega by e to the j 5 omega. Right? So here you can see it. Here's the omega on the linear scale, basically 1 times omega, and here we replace it by 5 omega. And this is basically then the phase of our all-pass filter, this 5 omega. Right? And here you can see this is our normalized frequency, and here we interpret the phase as a normalized frequency. Right? Yeah. So we can use it, for instance, to map it according to the so-called Bach scale used in psychoacoustics, which is kind of a logarithmic scale, where the low frequencies are wider distributed and the high frequencies are squished. Yeah, the common approximation of the Bach scale is this formula here. Again, it's basically function fitting. There's nothing fancy behind it. I have it from the Wikipedia page on Bach scale. And this goes back to Zwicker and Turner. They came up with this function approximation. F here is in hertz. And the Bach scale can be seen as an approximation of the changing frequency resolution over frequency of the inner ear of the human ear's cochlea. Right? So actually, they came up with the Bach scale trying to model what's happening in the ear. Yeah, because of the structure of our cochlea, the ear has different sensitivities for different frequencies and different signals. The signal-dependent threshold of audibility of the ear is called the masking threshold. Right? So anything below the masking threshold is inaudible. Anything above this threshold becomes audible. it has more spectral detail at lower frequencies than at higher frequencies, according to the Bark scale. So that's because the air has a better frequency resolution at low frequencies. And we can plot the Bark formula using the Python program which comes up here. So here I'm making my frequency, now the non-normalized, because this is really connected with physics. It's what's happening in the ear. So this is now in hertz, going from 0 to 20,000 in 1,000 steps. And here's my formula, right, the formula that we just saw. And then I plot it. X is the frequency axis, Z is the Bark scale, according to the Hilbert approximation. So here's then the result. So you can see frequency in hertz, and here is frequency in Bark, and you can see this shape. And when you think about this axis being negative, then it would pretty much look like our all-pass filter with A equals 0.5, right? If you just flip it down. And basically you have the same shape. And this is why it's so useful now to use this all-pass filter for the Bark scale. Yeah, so here we can now see that one Bark at lower frequency has a much lower bandwidth than at high frequencies. That means the ear can be seen as having higher frequency resolution at lower frequencies than at high frequencies. And maybe we can add this here. Observe the similarity of this curve to this negative phase curve plot of all paths for A equals 0. Yeah, so now we want to use this to design a filter for a system for hearing purposes, which has, for instance, we would like to model the masking threshold of the ear for any given signal by some linear filter, FIR and IR. Then it would be useful to give this filter a higher frequency resolution at lower frequencies, such that it matches the smaller details of the masking threshold. Yeah, so at lower frequencies we have finer details of our masking threshold. But if you look at the usual design methods, they distribute the filter details independent of the frequency range. We have as much detail at high frequencies than at low frequencies. For instance, passband width. When we have a passband filter, it doesn't really matter where we put the passband. We have the same effect on the attenuation. It doesn't really matter. So, it's independent. So we have equally distributed ripples, for instance, with the Reynolds method. Here we can now use frequency warping such that we enlarge the low frequency range and shrink the high frequency range accordingly, such that our filter now works on the warp frequency and sees the lower frequencies in more detail. Right? So we pre-warp our frequency domain and then apply the filter design. So the lower frequencies are more spread out in comparison to the higher frequencies. So we do the filter design in the warped domain and then warp it backwards. So how do we do that? For some frequency response, h of e to the j omega, we would like to warp the frequency, the normalized frequency omega, with some function phi of omega according to our desired scale, such that we get e to the h of e to the j phi of omega. Right? What we just saw. We warp the frequency scale. So this is exactly this principle of an all-pass filter, which has the frequency response e to the j phi of omega. Right? So here is all-pass. So we're almost there. So usually we would like to map positive frequencies again to positive frequencies, and we saw that phi becomes negative, hence we take the approach to replace z in the argument of our transfer function with the reverse of our allpass transfer function, because then the exponent becomes negative. Yeah, so basically here we already see how to do it. When we have a filter, and this filter has a structure which contains delay elements. Like an FRR filter, we have a delay chain, and then we have coefficients going away from this delay chain. So then we can replace each of those delays by an all-pass filter, right? Because of this substitution. And then the resulting filter is warped. Yeah, so in this way we replace our linear function on the unit circle in Z with a nonlinear warped function on the unit circle HAP. So you can see it again. The warped filter results from taking the linear filter applied to the case where we replace Z by this all-pass and minus 1. Right, because we have Z, so we need to have this minus 1 here. Yeah, and the resulting frequency response is then simply this. Right. So here this was from Z, this replacement substitution, and here we simply have this all-pass filter. Make sense? Yeah, so this was simply our frequency response of our all-pass filter with negative exponent.
So,
Yeah.
just a small doubt. Frequency warping is not necessarily for low frequencies, right? If instead of a equal to 0.5, we use a equal to minus 0.5.
Yeah, then you change the warping function.
Then it will warp the higher frequency.
Yeah, exactly. So for our dark scale, we still have to find out the correct A,
Okay.
which comes next. Yeah. So what does it mean for the filter implementation? We know that our FR filters always consist of many delay elements, as I just said. Z to the minus 1. For instance, here's an FRR filter where we just have the B coefficients and Z to the minus M. So we simply have a polynomial in the numerator. And then the warped version simply consists of replacing all the delay elements by all-pass filters. And this M means the M basically concatenation of filters. So here Z to the minus M means Z delays, and Z to the M means M all-pass filter in the cascade. Yeah, so this gives us a warped filter, but if you want to have a desired frequency response, now we have to basically warp our filter design. Right? To obtain a desired filter, we now first have to warp our desired filter and then design our filter in the warped domain. Right? Because the filter coefficients operate in the warped domain. Yeah, and also observe that the warping turns an FRR filter into an IRR filter because the all-pass is IRR. Right? It has holes. Yeah, an example can be seen here in this picture, or an example of such a design. So here we can see that we have a 12th order filter which successfully approximates the more detailed curve at low frequencies using the warping approach. So here comes the picture. And so the dashed line is the desired approach. So the dashed line, for instance, might be something like a mask threshold, or maybe from a hearing aid, a desired frequency response, whatever. So here the dashed is the desired, and the solid line is now the filter approximation using 12th order filters. And then you can see here the details and the low frequencies are not really covered so much. Also watch that this is the logarithmic frequency scale. Right? So here on this logarithmic frequency scale you can see more of the details at low frequencies. And so this filter is not doing such a good job here in the low frequency range. But when you apply warping, frequency warping, then here you get this solid line. You can see it matches much better the region of low frequencies, but then at the cost at some detail here at the very high end. Right. So usually this is actually much closer to what we want. Yeah, so this is from this transaction paper in 1999. And we did also some work here in Ilmenau about using frequency warping and low delay audio coding, which you can read about here in this conference paper. Okay, so we can continue with the next set of slides. Okay. Yeah, so here's a little example on low-pass filter design. So if we want to do, for instance, sampling rate conversion, usually we want to have a good low-pass filter, and if we want to do the sampling rate reduction a lot, we need to have a very narrow low-pass filter. So here's a very narrow low-pass filter, which has a cutoff frequency of 0.05 pi, right? It applies to max frequency, so it's actually quite narrow. And yeah, this frequency should be the end of the passband here, with the frequency warping close to the bar scale of human hearing. So maybe this might be some application to hearing aids. So first, as a comparison, we design an unwarped filter with 4 coefficients or tabs in with these specifications. So here you can see it. I do it in PyMap, and I'm using REMS. Right, so I'm using 4 coefficients, and here is the band specification. So here is 0.5, which is Nyquist in this case. Here's the passband, and here's the stop band. So here the stop band starts after some transition band. So this is the transition bandwidth. Right. Then I have weights. So this is passband is the first band. Stop band is the second band, so the desired output is here 0. Then gain, weight is 1 for the passband and 100 for the error in the stop band. So this usually gives us a good filter, like 40 or 50 dB attenuation. So in this case, we can take a look at the resulting filter here with the print. See unwarped, coefficients unwarped. Here are the filters. And here are plotted, and you can see they look kind of strange, right? There's very small values, and then they go down. Here it's almost 0. doesn't really look like a sinc function. There's no similarity to a sinc function. And then we can use fractional to plot the frequency response. And this confirms our suspicion that this is not really a good filter. So first, it basically has no pass band. It starts with minus 40 dB, and then it also really doesn't have a stop band because it has the same attenuation. Right? It's not doing any filtering basically. Yeah, so this is basically useless for application. So now we would like to design a low-pass filter using frequency warping with a warped cutoff frequency. So now we need to warp our specification first. Yeah, first we have to compute the all-pass coefficient A for our all-pass filter, which results in an approximation of the Bark scale according to reference 1, equation 26. We have this formula here. Fortunately, they gave us this formula, so that's nice. And then we just use it. Here's this sampling frequency in kilohertz, and we use it here in our Python program. So here you can see it. I'm just typing in this formula here and then execute it for our FS of 32 kilohertz. You can see it, 32 kilohertz is our assumption. And the answer is then 0.85. Well, it's actually close to 0.5, but it's not so far away from 0.5. And it also depends on the FS here. So then in the warped domain, our cutoff frequency is applying this warping phase function, right, to our cutoff frequency of 0.05 times pi. Remember, this was our desired cutoff frequency. And this is the A, 0.85. Make sense? So this is basically the important part here. We warp our cutoff frequency. So basically, we warp our specification for our filter. Right? And as a result, we get a new cutoff frequency of 0.6 in radians. And so this is about pi over 2, roughly. So it's now not so narrow band anymore. Now it's more like a half band filter. Right? And we already have some experience with half band filters. They are not so difficult to design. Right? So now then we take this warped frequency. We do a normalization for Ramus. So here we divide by 2 pi for Ramus because 0.5 was a Nyquist. And then we get this new factor here. Put it into the Ramus, here with the warp specification. Strictly speaking, I would have also needed to warp this beginning of our stop band. I just did an ad hoc estimation here. Right? But the main part here is the warping of the cutoff frequency. Yeah, so Ramus, now in C, coefficients. Again, I plot it. And I get these 4 coefficients. And at least they have some similarity to a sinc function. Right? It's at least like, looks a little bit like the main lobe of a sinc function. And you can also take a look at the frequency response, and indeed, this looks actually somewhat like a low pass filter. So here at the beginning, you have a pass band, and then here you have the transition band, and here you have the stop band. The stop band has maybe 40 dB attenuation. You know, 40. It's not great, but at least a low pass. Right? It's doing something. And it has linear phase because it's an FIR filter. Yeah, so this is the filter that we obtain from the C coefficients if we don't replace the delay by all passes. And now we can do this replacement. We replace all the delays by all passes. Right? So here, instead of Z, we use this 1 over AS on all pass. So here you can see how it looks like. We have 4 coefficients. right? And meaning we will have 3 all-pass filters. And the implementation now has to be done independent of L filter, because L filter always has those delay elements. So basically here we have to do it manually. So here we can see the B and the A for our all-pass filter using our A that we just determined. Here we can see the impulse response. Here we have our delayed X, or all-pass filtered X. So here's after the first filter, here after the second filter, and here after the third filter. And this is the output then of our warped filter. You can see here C0 plus times X. X is our impulse. Then plus C1 times Y1, the output of the first all-pass. C2 times the output of the second output, all-pass, plus C3 times the output of the third all-pass. So now we have the impulse response for our warped filter, and we can apply Frexy to the impulse response. This is an impulse response of length 80 zeros, and this is the result. So now you can see it actually looks quite good. So we have a narrow pass band, here you have a transition band, and then we have a stop band compared to a pass band of maybe 50 dB. So this is now actually a useful filter, right? A very narrow band, useful low pass filter. A very low, a very nonlinear phase, but that's because now we have an IR filter. That's why the phase became very nonlinear. So it's actually not so bad filter. Okay, yeah, questions at this point? I guess this is a good point to stop and continue next time. So thanks for your attention and have a nice Christmas vacation.